next talk for today is Iván Díaz. It's our colleague, Iván Díaz from Do It Now. And he is going to explain the AI in biomedicine, trends and challenges. Thank you so much.
Okay, as Jordi said, I am Iván Díaz, and I work for Do It Now, and I will do a presentation on AI on biomedicine, and we will cover the basic technology, new developments on the field, use cases, and concerns and legislation to address those. And there will be many topics to cover in this presentation. And this presentation was created by Guillem de Valles and me. Here you can see our photos. And Guillem de Valles is a computational biologist, and he works and lives in New Zealand, but he can collaborate with us and be in the same team. It is a small everyday miracle of modern technology, and he works deploying scientific software where we are still sleeping. It is a superpower. And the one in the right is me, and I do mostly DevOps and sysadmin work in the biomedicine field. And if you want to summarize my career in a phrase, is I do support for scientific for scientists and scientific computing. And so what exactly are AIs and why everyone is hyped about those? So basically, AI is a term that has encompassed a lot of different technologies across the years. We have rule-based expert systems, neural networks, machine learning, deep learning. But today, it basically means normally large language models, LLMs, that are a transformer, multi-layer perceptron mixed paradigm, and they work basically by getting a string sequence of input tokens that can be words, not necessarily, and predict the next most probable one in the sequence. Is basically what they do. There is a lot of complication about that simple paradigm, but this is the basic functionality. And there are also diffusion models that work with continuous data, like images or video, and those can also be integrated with transformers and LLMs. That's why you can input a prompt to those, and are based on a noisy architecture. That means that they start with very noisy data, and they noise it to arrive to the desired output. And both have two phases. One is the training phase, that requires a lot of compute for training GPT-3. They had to use 1,024 GPUs for 30 days, and it was like 300 zetaflops. That is 3 times the power of 25 flops. That is a lot of computation. We saw in the earlier presentation that it was an issue, and it has a sustainability impact. And they can be trained by using a labeled corpus of data, or by reinforcement learning either on humans or other LLMs. And then you have the inference phase, that is when the users input a prompt and get an output. And in this phase, you don't have any learning. So you can put new data in their context, but there is no intrinsic learning. So why are we now in an AI boom? Well, there are a lot of milestones in this history, but there are 4 that are particularly important. The first one is the use of recurrent neural networks for natural language processing. And we have, for example, the word-to-big vector embedding technology that represents words as vectors in a highly dimensional manifold space. That space encodes different semantic capabilities in different dimensions. Those original systems had generative capabilities already, but when the output grew very long, they tended to give gibberish as output because they lost track of what they were doing. In that way, there was a very seminal 2017 paper by Google, Attention is all you need, like the Beatles song, that introduced the transformer architecture. Basically, this architecture reintroduced the attention paradigm. There you can see an example in which we have a sequence of input tokens, and the transformer determines which token affects the meanings of each token in the sequence, in which dimension and how much. And you have also several attention headers that each focus on a different semantic relationship between the tokens. This is encoded in several matrices with keys and values that are all changed in the training. And with that, it solves part of the problem with the context, creating context window, but it was still not perfect, and it was not until the GPU improvements in computation allowed those models to scale to billions of parameters. That causes a lot of improvements and for emergent capabilities to appear in the system. But the real spark in the AI boom, the thing that caused the AI boom to happen, was the use of chatbots. There you have the first chatbot, that was ELIZA in the 60s. That was an extremely primitive system, but people thought this was a real person they could talk with it about their life and their problems and whatever. And this psychological reinforcement and various interface that made that everyone could use it made a massive adoption and really caused the boom itself. In the field of biomedicine, we can see a different milestone. In the left, the two first, you can see the advances in artificial vision. For example, AlexNet and the first authorized system to do diagnosis of diabetic retinopathy without human intervention. Then the COVID outbreak caused a lot of adoption on the field, for example, for the clinical trials of AstraZeneca. Then we have Alphafold that we will cover in more detail afterwards. Adoption of foundational models, and some of them that were geared for the field application, like BioGPT and PubMedVer. And in the last times, we have seen increased adoption of these techniques to do generative design of drugs and therapies. So what other current developments are relevant for the field? Well, the first month of this year, DeepSeek was introduced, and it was a total surprise. It is a state-of-the-art reasoning model from China that demonstrated that all of this could be done with much smaller compute, both in training and in inference. The figure they gave was $5 million versus $100 million. And there are a lot of optimizations they did to achieve this, including minimizing the intervention of humans in the training process. And they did a lot of open sourcing of both the weights and the publications. They did like 1 paper per month. For the field, apart from being able to use on-prem AI capabilities on very small institutions, this enabled a push for openness and more competition on the field. But it also has problems like that has security vulnerabilities, it has less conformance with EPDR and so on. It is easy to jailbreak, and it was trained against competitor models, so it can be a legal problem in that way. For May of this year, they were to release an R2 version, but it still didn't release. It is not clear when they will release, and it will have advancement in multilingual and multimodal reasoning, better source code generation, and improvements on self-training. The DeepSeek R1 is a reasoning model. Exactly what is a reasoning model? Well, basically LLMs predict the most probable token in the sequence. And this is fine for small problems like which is the capital of France. But for example, you have a computer science or mathematical problem that has to be done in several discrete steps. It doesn't work so well because it uses the same compute effort for both problems. One early hack to address this was the chain of thought that was giving a prompt that gave an example of how to itemize the problem in smaller problems and how to reason about it. And the reasoning models both generalize and use other techniques to control how much compute power is used in inference for these problems. This costs a lot more cost both in training and inference, but for those type of problems, it improves the output a lot. Another very important technique is the retrieval-augmented generation. That is a technique to address the problem that the context window, normally it is in the 100,000 token range, that is like 100 pages of text, and if you have reference documentation that it is larger than that, then it will not fit the context window. Then RAG what does is to ingest those documents using an embedding model that doesn't have to be the same as inference, and store those vectors in a vector database, and then a retriever from the prompt gets the vectors that are more close to in the database to the vectors on the prompt, and retrieves the original documentation and copy-pastes it in the prompt. This is a technique that allows to use large amounts of data without having to curate and update them, without having to do a retraining that can be very costly. And it is crucial for the field. For smaller amounts of documentation, you can use also cache-aided generation that basically pre-processes the input documentation and then stores the state of the transformer and reloads it when you want to do a prompt. And this has less latency because you don't have to search the database. But if you have a very large documentation, it doesn't work as well because the state doesn't retrieve all the information. We will enter now in the use case section, and the most famous use case of AI in biomedicine is protein folding, and especially Alphafold. And Alphafold is a system that basically, from a sequence and a string of amino acids of a protein, derives the quaternary structure. That this is the final 3D folded structure that is extremely important for X function. There are even diseases if the protein doesn't fold correctly. And it's not an LLM, it is more of a generative system that has two cross-attention, one for chemistry and physics information, another one from evolutionary biology data, and interchanges information between the two to get the final structure. It won the CAST-13 challenge, that this is a yearly challenge for algorithms for protein folding, and not only that, it made the number of predicted protein structures to go from 150,000 to 200 million. That is mostly all the proteins we know nowadays, and that made it won the last year Nobel in chemistry. This type of technology not only allows to monitor and evaluate proteins and other molecules for their medical uses, but also to create new ones from scratch, de novo. And there are a lot of companies in this space. It's a crowded space like this slide, basically. And here we have an example, and this is an interesting one because it uses several tools. And this is to finding a hit molecule, an enzyme for the salt-inducible kinase 2. That is a molecule that is involved in glucose metabolism. And basically, here they use Alphafold to determine the rough primary structure and then chemistry 42 to determine where the molecule falls upon itself, the hinge course. And then they use an extractor activity relationship iterative process to determine which configuration of the molecule is most efficient. And with that, they get a molecule that is optimally efficient for inhibiting that molecule. Other use case is image processing, and there is a lot of applications here. In the bottom, we see an example of diagnosing mammary cancer. That is very difficult to diagnose because there is a lot of variabilities and the nature of the tissue. And that case was a very famous one from the MIT that they diagnosed a case 4 years before onset. In the right, we can see also it's used in chirurgy with robots for chirurgical operation. And in the left, we have an example of cell counting. I told bacteria in the first iteration, but Guillem told, no, they are eukaryotes, they are human cells. And the top one is a system to track the behavior of animals, in this case, rodents and insects, and it can track individual specimens and see the behavior for several purposes. Other use case that we provide 2 examples here is generating clinical documentation. And there are 2 very different examples. One is the NovoScript from Novo Nordisk. That is a system to compile clinical study reports that are documents with several hundred pages that are for regulatory purposes. And they need a lot of documentation. So what they do is with RAG ingest a lot of the documentation to compile those final reports, and OCR them and insert it into a vectorial database, and with that they can generate the final document. And with it, they claim they could make a process that took weeks in mere hours and with much less human intervention. Another very different case is Signatera from Natera. That is a system for determining personalized patient diagnosis testing for patients in cancer remission. And it uses RAG to get all the documents from the patient history and ingest them into a vector database. And with that vector database, they can create pipelines in AWS Healthomics and create custom pipelines to do a customized version of how the patient's life history and prognosis. Another generative task is scientific literature review, and it not only includes literative review, but also discovery. But for that, you should use web search, because if not, the LLM can hallucinate the papers, and it would be very bad to get hallucinated papers in your research. And it can also do summarization to see which could be interesting for your purposes, and fill in research gaps. For example, we use Gemini to see that this presentation had gaps in the coverage. And it also can help with the basic reading and editing tasks, data analysis, and citation management. That this is a particularly arduous and tedious part of writing papers. Of course, another generative task is code generation. And for that, there are a lot of LLMs in the market. And for programmers, web coders, it allows them to concentrate in creative tasks instead of wasting time on writing boilerplate code. But it has the problem that the code that it produces can have vulnerabilities, not be reliable or work correctly, and need debugging, and can also increase technical debt if it doesn't fit the best practices and not adjust to the style of the organization. And it can also be a crutch for novel users that rely too much on the system and then don't learn to code properly. In this way, there is a debate between augmentation and automation. Augmentation would be that the coder uses the LLM as a helper, and automation would be that the LLM does most of the job, and the coder vetoes it, basically. And nowadays, there are code agents in this space that do very complicated tasks, like writing merge requests and even parsing images to debug code errors and automate the curation of entire code bases. And not all is flashy stuff. LLMs can also help to generate your normal documents and spreadsheets. And nowadays, they are integrated in most collaborative suites and tools, even in Windows Notepad. And it is a big incentive for organizations to have an internal vetted solution that doesn't incentivize users to filter data to third parties. This is one of the concerns that we will cover with the regulation that intends to fix those. And the primary concern in the field, of course, is the security. That is an everyday concern, and includes data leakage, filtering sensitive data to third parties, and that the AI, for example, promotes bad security practices. And also, we have the privacy concern, in which, for example, an example is the privacy surveillance. For the Microsoft Recall example was a particularly notorious one, doing personal data collection that doesn't do minimization, that is, that it doesn't get the minimal amount of personal data that is required for the task, and that is not transparent. And there is a temptation of removing the human for the loop. That it can be bad because in some cases we don't know how the LLM arrived at the conclusion. Other concerns are systemic biases, hallucination, and a very new one is sycophancy, that the AIs can be very nice. That it means that even if you give them a very bad idea in the input, they can tell you that it is a particularly good one, and it was so bad at a problem that OpenAI had to do a rollback of GPT-4o because it caused problems promoting delusional thinking in some users. Well, to address this, there is some regulation now, and the most complete one is the EU AI Act that does a classification of risks in 5 tiers, and from unacceptable, that is banned, that is almost from science fiction, and the medical systems are normally in the high one, that is transparency, that you know that the output is from AI, oversight and safety before commercialization. And it includes fines of 35 million or 7% of annual global turnover in the worst cases. And from the US, there is no currently a central legislation. There are only federal laws. And the Colorado one, for example, is for algorithmic discrimination. That is, the AI doesn't give me a credit. And then it is one to avoid AIs for cloning the voice of Elvis. And China is basically the first one that there was, and this is only to adapt the AIs to existing legislative frameworks. But in general, in this field, there is a lot of work to be done to improve the legislation because it is very sparse still. And with that, this presentation is finished. Thanks for your attention, pun intended. Time for your questions, you have any.
Thank you so much. We have time for a couple of questions.
Well, since there are no questions, I would like to add one concern to what you just said at the ending topic, which is reproducibility.
Which one?
No, from all the concerns that all these things have, and I would like to add reproducibility or reproducibility.
Yeah.
And I'm going to put a perfect example. You've talked a lot about Alphafold. I used Alphafold in daily basis. You cannot nowadays install Alphafold 2, the one that won the CASP contest. You cannot. It doesn't install. It gives you lots of conda errors of impossible to match different packets, blah, blah, blah. And it's been like this since a long time. We managed to do a workaround with the Docker requirements, whatever file, but now not even that works. And so you have the software there, but it's installed in all machines because back in the day it installed, but you try to install it now and you cannot. So we are generating lots of tools and they look great, but then when you go to use them, you find that you cannot use them.
Well, that is not exactly an LLM-specific problem. I thought that you were referring to that they didn't give the same output 2 times. That is because they are probabilistic systems. But well, yeah, that's a concern in all software bases. So LLMs aren't immune to that problem. This is one other more concern to have in mind.
Anything else? No? Okay, so let's thank again Iván.